Okay, so when you have this, I'm gonna have to say one more things. We have damping. We have a damping in the building. Okay, damping is something that dissipate energy. Okay, damping dissipate energy. Something dissipate energy. So if the damping does not exist, or there's something that dissipate. You know what dissipate means? Make your building exhausted. So the building start vibrating and stops in sometimes, in few moments, right? Why is that? Why building do not vibrate forever? Because you have a damping mechanism. You know, we've seen a lot of damping around us, right? We have a hinge at the door, so it stops the door, right? We have a door here. We have a door here. We have some hinges over there, right? So when you doors open and doors close it automatically. Otherwise, this door open and going in a cycle without stopping. The door will never stop at where it's supposed to stop if it doesn't have any damping, or hinge provides damping, right? We saw door damping, door hinge, right? Door hinge provides a damping so that door opens and goes down and stops where it's supposed to stop. Beautiful, isn't it? So that's a hinge and damping. So damping is very important for things to stop. Okay, same thing for building. Building has a inside damping. So this damping stops building vibration, building movement in very short second, right? So when you have a damping, the more damping, the faster stopping, right? So that you have damping here now. Let's take a look at damping in response spectrum. Okay, see the response spectrum will look like that if you consider a damping. Okay, here, this is the damping, 2% damping. Okay, and this is the damping with a 10% damping, right? So, and this is 20. So when you have more damping, your response acceleration decreases this way. So the more damping, the more decrease in your earthquake response in all acceleration, velocities, and displacement. Maybe if you don't have any damping, then it may go like huge, right? So this is no damping, zero damping. Okay, so and look at that. When you are here with the t equals 0, what this value is called? This value is called a PGA. And when you have a big period, and all the responses should go 0, because you don't feel anything, because the building is very flexible. Okay, and in the middle, you are increasing your response towards a resonance and goes down, right? So resonance is somewhere here, right? So here maybe it depends. Resonance depends on which soil your building is on. If you have your building on a very stiff rocks and stiff soils, then this will be around 0.2 to 0.5 second at T. But if you are in very flexible soil, filled in flexible soil, then your peak will correspond to like 2 seconds, 1.5 seconds to 2 seconds. This is what happened. All right. So it depends on what type of soil you are having underneath of your buildings, but the shape of the response spectra looks like all same. And let me explain the damping ratio one more time. Damping ratio is a fractions, right? Fractions, okay? The damping ratio is a fractions of critical damping. So we call damping ratio Cauchy equal 0.2. Okay, 0.2 means equal some damping coefficient over CC. C over CC. The CC means critical damping. Critical damping. Critical damping. So what critical damping means? Critical damping means a damping you can stop your building at one cycle. But how can you do this? If you have a big, very big, huge damping, then you can make building stop at one cycle. Do you understand? But we do not have that damping in reality, in nature, because the damping is not possibly existing around us, right? Anyway, this is a imaginary damping. You just say that critical damping for that, okay? So you're saying 0.2 or 20% damping means you have a 20% of fractions of CC, 20% of CC, in other words. If you say 0.05 critical damping, then you're saying that 5% damping fractions of a CC, which is critical damping. So you have 5% out of CC, which is critical damping. So this damping ratio, fractions of critical damping, okay? 2%, 5%, 10%. So your concrete building in your projects, the low-rise, okay, low-rise concrete building, you may use a 5 to 10% damping, okay, low-rise concrete building, and building. A high-rise building, you're damping really small, like 1% to 1.5%. Don't forget. Okay, let me just say it again. You're having a low-rise building. Low-rise building has very different for these two cases, concrete building and steel building. You have probably 5% to 10%, maybe a little over 10% for concrete or low-rise building, and 2% to 5%. Okay. Okay, take a look at a damping ratio. Damping ratio is a fraction of critical damping, as I explained. So CC is critical damping. Again, what is critical damping? Critical damping is the damping can make your building stops at one cycle. So this is huge damping that we don't see around us. But this is a damping, theoretical damping, so that when you're talking 2%, then this is 2% of critical damping. People don't say 2% of critical damping all the time. When they say 2%, then you have to understand that means a 2% of critical damping. Okay, and I said that before already. Okay, here we have a damping tables, and the damping changes depends on the type of structure. So you have a steel buildings, the damping ratio is going to be between 2% and 3% for weldings, and you have 5% for bolt. Okay. And when you have reinforced concrete building, the damping ratio is going to be a little higher. So we have from 5% to 10% with the shear wall. When you have shear walls and you have very much of concrete walls inside, then you have a damping which is 10%. If you don't, then you could have still 5%, right? So that the shear walls and concrete elements in the building will contribute to higher damping, something you see over there, okay? And this is basically for low-rise building, okay? When you have a high-rise building, it's more complicated. High-rise buildings, damping is very small, okay? Regardless of material, which means that it doesn't matter whether you have a steel building and not much concrete building. The high-rise building damping is about 1% to maybe 1.5% damping. Okay, so what can you say? We interpret taking a damping ratio for high-rise building so that it's really difficult for us to stop high-rise building vibration once it started to vibrate, because the damping 1% and 1.15%, 1.5% is very small damping to stop the building in very short time. All right, but low-rise buildings are okay. You have a rather large damping. It depends on materials for 5% to maybe 10%. Right? That's okay, and it's enough to stop your building in very short time. But something are different when you think of a high-rise building. High-rise building is very hard to stop because your damping in it very small. So what we're gonna study that later in probably when you do your projects. So we need to introduce a artificial damping. Artificial damping. The damping we create artificially in the building so that the building can stop as soon as possible. And we can add artificial damping, man-made damping into the building, probably up to 5 to 7%, which is pretty high, right? So that you can stop your building as soon as possible, as quickly as possible. So this damping is very important for you to design a high-rise building. When you get to Midas project later, your buildings never stops, or your building's diffraction is very high, so you cannot stop, you cannot start, and you cannot finish your building's motions. The reason is your damping is very small. Okay, that you need to think about putting some artificial damping. So, in reality, understanding and determining damping ratio is very important. If you make a mistake in putting damping ratio in real large scale when you work in the future in the company, then you're making very big mistakes because your building stops very fast and your building diffraction is very small. You remember what's the limit of the building deformation that you use when you design a high-rise building? I said, if you remember, delta equal L over 400 through L over 600, right? So if your damping is mistakenly input into the building or your diffraction calculation is wrong, then you are in big trouble, right? So you always have to discuss and carefully determine the magnitude of damping and the damping in the building so that you calculate your diffraction accurately, right? So when you put very small damping like 1% and 1.5%, you're okay. You're not making mistake, right? But you're putting 4% and 5% in the beginning, then you're wrong. So this is easy to see whether you're doing okay or whether you're doing not okay. right? So, and don't forget, you just have to put the 1% to 1.5% of natural damping, and you can increase by putting a artificial damping. Okay, I'm not gonna repeat anymore. I hope this is enough to explain what damping ratio can do for you. Okay, let's go back to the response spectrum. And now you don't want to forget about the damping ratio. It's very important. Okay, now let's make a conclusion on response spectrum analysis, right? The response spectrum analysis and definition. Okay, now we understand how to make a response spectrum analysis based on period, an x-axis, and for different damping ratio. Okay, the damping ratio is what again? Damping ratio is the quantity that makes your building slow down. It dissipates energy. It uses energy through the heat energy and sound energy and all the energy, right? It just gone and stop your building. So energy is used to stop your building. And energy is used by heat, by sound, and all that, so that your building lost the power to move on vibrations. Okay, so this is what damping will do for you. It's just very good thing for you when you design the building. Okay, so definition of response spectra right here. This is very important. Maximum response. Okay, so we only check maximum value. We're not interested in any other value but maximum value, as we talk about the maximum value. See? Maximum value exists only one location on one earthquake for one period and for one damping, right? So you have a maximum response. The what response are we talking? We response three things, right? Three physical quantities: accelerations, or velocities, and displacement. We really don't care. But engineers love to work with the accelerations, okay? Accelerations. But you can use a velocity, you can use a displacement when you design your building. But most of the engineers is familiar is working with accelerations right there. Okay. And this maximum response of this one of these three things, for example, accelerations, as a function of a period, your acceleration changes. Your magnitude of accelerations changes where period of building changes, right? So when your period of building is very small, then you are here at PGA. When you are having a very big period of the building because your building is very flexible, then your acceleration response goes to zero, like this, right? And here you have a resonance, plateau, resonance conditions, right? So your maximum acceleration changes as a function of your building period, okay? And also your maximum response of your accelerations, velocity, displacement, whatever, will reduce as your damping increases, or your response will increases as your damping ratio decreases, vice versa, right? So now do you understand? And this is for a single degree of freedom system, all the single degree of freedom system. So single degree of freedom system is nothing more than when I plotted a few minutes ago. Okay, so here, we start our discussion with one building like that. The math is lumped at the top of the building, and we consider the stiffness, whether it is very stiff or very flexible, right? It's like a one-story building, right? So the top of your map has only one freedom to move which directions? Yes, horizontal directions. Your building can only move horizontal directions. It is called a single degree of freedom system. It's easy, isn't it? So your definition of your response spectra is a for one-story building, which is one single degree of freedom system. Okay, now understand the definition of your response spectra. Okay, let me repeat one more time. Your response spectra is maximum response of your three things, either accelerations or velocity or displacement. Okay, I'm not going to tell these three things anymore. Okay, because you feel tedious, right? You feel tired, right? Okay, so the maximum response of the single degree of a freedom system as a function of period and damping ratio. Okay, I'll give you a few seconds. To try to memorize the definition of response spectra. So don't try to memorize. Don't try to understand. Okay. What is your definition of response spectra? Okay, I'll give you a few seconds. Okay, you got it, right? The maximum response of acceleration, velocity, displacement of a single degree of freedom system as a function of damping ratio and building period, right? So why do you need this? Because you need this in Midas input. Okay, you have two ways to input seismic load in Midas. Okay, the first way is to use a response spectra. So you put some parameters that can define the shape of response spectra in the Midas. Okay, and you learned the concept of response spectra. So it's easy for you to handle those things in Midas input. The second way to put seismic load in Midas is to understand and calculate seismic parameters. And that's what I'm going to explain in next lecture. We have some parameters to understand, but this is totally different way from response spectra. But that's easy. If you listen to my video clip next time, one more video clip, you will understand how to pick up those parameters to put seismic load in Midas. So now we have two ways. All right.